Hello and welcome to Statistics 5, Preparing to Test for Differences, Populations and Samples. Last week was a bit dry. This is an important video and it explains some difficult concepts. You may want to ask questions about them. Understanding them is essential prior to us actually doing some statistical tests, which we will do next week. For this you will need SPSS 19, you will need the new data file fluid.sav below. Unfortunately there are two chapters in the core reading this week, Population and Samples, Chapter 4 from Statistics at Square 1 and Statements about Probability, Chapter 5. We will come back to Chapter 3 in the future. These data deal with a new scenario. It is about post-operative fluid management. There are two main variables, control_fluid and treat_fluid, and these are the total daily intravenous fluids that patients in a control group who receive standard fluid management versus patients in a restricted fluid management group received. For the purpose of this exercise and the concepts that we're going to try and get over today, the variables are slightly different. There is control_fluid and treat_fluid, which represent the population of all patients in a geographical area. Let's call it Scotland, that's where I am, over the course of a year. These two variables have 500 rows in them, each which represent an individual patient who had their total post-operative fluid intake by intravenous fluids measured. There are another 5 variables relating to control and 5 variables relating to treat. And these are random samples from the population. So control sample 1 has 50 random patients that have been selected from control_fluid. Control sample 2 has a different sample, which is this time 100. Sample 3 contains a sample from the population of size 200, sample 4 of size 300, and sample 5 of size 400. And it will become apparent as we go on why I've done this. So what we're going to be discussing today is the difference between a population, the difference between looking at all patients in a population versus a sample, that is taking a random sample of patients, a smaller number than the population from the population, and trying to infer something from the sample about the population as a whole. We're going to be talking about the standard error of the mean, SEM, which you may have seen and may have wondered what the difference between that and the standard deviation is, or you may not have even noticed, and why this is essential to understanding what we mean by a confidence interval. So by the end of this video, I hope you know what the SEM, the standard error of the mean, is, and you've got a really good grasp of what a confidence interval is. We are going to be introducing a new function called explore. Load fluid.sav into SPSS, and this is what you should see. So let's carry on and do what we would do normally and get some simple summary data. Analyse descriptive statistics frequencies, untick the display frequencies table and scoot across just the control variables, and you want the population control fluid and the 5 samples. Go to statistics and include the mean and the minimum and the maximum as normal, and also include the standard deviation. Click continue and click OK, and this is the statistics table. So first of all, why have I set things up in this way? Well, usually we don't have access to a full population's data. So normally we wouldn't have information about, in this case, post-operative fluid intake for all the patients that we are interested in. We would only have data on a sample of patients, and that sample might be in our hospital or 2 hospitals or 3 hospitals, but it would rarely represent all of the patients in the group that we are interested in. And what a lot of statistics deals with is how to infer from a sample of patients conclusions which apply to a population of patients. And this is what we're trying to explain. This is the concepts required to do that are what we're hoping to explain here. So let's have a look at what we've got here. We've got our population statistic control fluid, and we've got 500 cases in that. In sample 1 we only have 50 cases, in sample 2 100 cases, in sample 3 200 cases, in sample 4 we have 300, and sample 5 400. And I've created these samples by randomly sampling from control fluid. So I've just told the computer to take 50 samples in sample 1, to take 50 samples at random from control underscore fluid. In the population variable, control fluid, we've got the mean and the standard deviation, 4.46 and 0.99. Now we wouldn't normally know this information. So let's think about these other 5 variables, the sample variables, as if they were different trials. So the first one's a small one, the second one's a bit bigger, the third one's maybe multi-centre, the fourth one's definitely multi-centre, the fifth one has captured almost the entire population, but there's still 100 patients that for whatever reason that trial wasn't able to gather data for. How good are each of those samples, or studies if you like, at estimating the population mean? So in the population, the mean fluid intake for all patients was 4.46. In each of our studies, how close do they get to the truth, which is 4.46? Well, our small study number 1 is 4.3. In our second study, which is 100, it's actually a bit worse, just by random, 4.26. When we include 200 patients, we get to 4.40. When we include 300 patients, we get closer still to 4.49. And when we include 400 patients, we're up to 4.458. Remember, these are random samples. I haven't set these up in any way. These are just totally random samples from the population variable. Let's add some histograms, analyse descriptive statistics, frequencies, charts, histogram, continue, OK. Histogram 1 is our population data. This is the true distribution of fluids within our population. Our sample of 50 is an approximation of that population, and it's not bad, but it's not that great either. As we go down, getting more and more samples from our population, the histogram looks more and more like our population histogram until we get down to a sample of 400 in sample 5, which looks pretty like the population. Let's go back to our statistics box and look at these means again. In sample 1, the mean was 4.3, which was quite far off our population mean. Now that was just by chance that it was far off. If the 50 patients sampled from the population had had a mean of 4.46, then it would have hit it dead on. But, and this is the crucial point, the greater the number in your sample, the more confident you can be that the population mean is close to your sample mean. I hope I've explained that well enough for you to follow up until now. Please ask questions if I haven't. I hope now what will be kind of developing in your head is what would be very useful is if we had a number which would tell us how confident we can be that our sample mean is close to the population mean. And that number is called the standard error of the mean. Now, we have talked about the importance of the number in the sample, and have a look at statistics at square one and see that the standard error of the mean is calculated by dividing the standard deviation of the sample by the square root of the number in the sample. That sounds a bit complicated, but if you think about it, all it means is that number, the standard error of the mean, gets smaller and smaller and smaller as the number in the sample increases. Let's do a quick example of calculating the standard error of the mean for sample 1. So as you'll see in statistics at square 1, you take the standard deviation of the sample, 1.0097142, and divide it by the square root of the number in the sample, so the square root of 50. So the standard error of the mean in sample 1 is 0.143. Now go to Analyze, Descriptive Statistics, Frequencies, Statistics, and here you'll see SE mean, which is standard error of the mean. Click that and click Continue. And have a look and see that standard error of the mean for sample 1 is 0.143, exactly the same number as you've just calculated with the calculator. So the standard error of the mean tells us how precisely our sample estimates the mean of the population. Have a look at the estimates for the different samples with increasing numbers. For 100, the standard error of the mean is 0.1. For 200, the standard error of the mean is 0.07. For a number of 300, 0.06, and a number of 400, 0.05. How can we convert this into something more meaningful? Well, this is where we meet a confidence interval for the first time and have a read about it in statistics at square 1. For this, I want to calculate a 95% confidence interval for the mean of sample 1. By looking at the appendix of statistics at square 1, you can see that a 95% confidence interval is associated with what's called a Z value, and the details of that don't matter, of 1.96. So to calculate the 95% confidence interval, and we'll talk about what that means in a minute, of the sample mean in sample 1, we multiply the standard error of the mean by 1.96. So let's do that for standard 1. Take the standard error of the mean, which is 0.143, multiply it by 1.96, and you get 0.28. So that's the 95% confidence interval in one direction. I can add that to the memory of this calculator, then take the mean, which is 4.30 plus 0.28 is 4.58. I'm just going to jot that down, 4.58, and 4.30 minus 0.28 is 4.02. So the 95% confidence interval for the sample mean in variable 1 here is 4.02 to 4.58. What does that interval actually mean? Well, it means that if we randomly sampled in a similar way to how we've done it in sample 1 with 50 samples from the population 100 times, then in 95 of those samples we would expect the true population mean, which is 4.46, to lie in that interval between 4.02 to 4.58. Let me say that again. If we repeated sample 1 100 times, so if we repeated that random sample 100 times, in 95 of those samples we would expect the true population mean, which is 4.46, to lie within that interval, 4.02 to 4.58. We can get SPSS to calculate that 95% confidence interval for us by going to Analyse, Descriptive Statistics, Explore, and this is a function that we will use quite a lot when we're looking at grouped data when we go back to the hernias, but at the moment we just want to scoot across sample 1 into the dependent list. You can turn off plots for the moment and go into statistics and ensure that it's 95% confidence interval that's specified. Click OK. And you can see here the 95% confidence interval, the lower bound is 4.01 and the top bound is 4.58. There's a rounding error with our 4.02 to 4.58 because we didn't put the whole length of the standard error of the mean, which is included here, 0.142795, into our calculator. So from that, I hope you have a better feel now for sampling from a population, the importance of the number in the sample, how the mean of the sample relates to the mean of the population, and our confidence in that mean is defined by the standard error of the mean. And we can convert that into a confidence interval, which gives us the confidence that the true population mean lies within that interval. Have a look at the 2 chapters in Statistics at Square One, and please pop any questions onto the board.